Okay, so we're going to finish up our notes on functions of several variables. So we looked at we started with the elliptic paraboloid. We talked about the ellipse and then how it's made up of the parabolas. We looked at finding the axis where it crosses the x, y, and z axis. I did my beautiful drawing and then had a different view, not of my personal drawing, for you to look at. We looked at finding the domains. We talked about how when we think of domain in like the xy plane, we usually think of the domain in terms of just x, but when we're thinking of domain when we're looking at 3-dimension, we look at where it is going to work for the ordered pairs for x, where all ordered pairs will work for x and y. Alright, so we did several of those. And so then the next topic we were going to look at was the level of curves or contour curves. So the level of curves of a function, let's say level curves. So level curves of the function z equals f of xy are two-dimensional curves. So level curves of the function are two-dimensional curves. We get by setting z equal to k, where k is any number. So the equations of a level curve, equations of the level curves are f of xy equals k, because if z equals f of xy, then k equals f of xy. So sometimes the equation will be in the form of f of xyz equals 0. So let's write that. Sometimes f of xyz will equal 0, and in that case the equation of the level curves are f of xyk equals 0, because z is k. Remember, with equality it's is. You've probably seen level curves or contour curves before. If you've ever seen like an elevation map for a piece of land, it's nothing more than the contour curves for the function that give the elevation of the land for that area. So we can at least try to graph contour curves. We might not be able to, we probably won't be given a function for elevation. But let's look at a quick example. Okay, let's identify the level curves of f of xy is equal to the square root of x squared plus y squared. Okay, first of all, let's think about what this is going to look like. So if you think back to the quadric surfaces, the handout I gave you, if you look through the slideshow, so this is the upper portion of an hourglass, a cone shape. So it didn't ask us that, but of course, you know, trying to pull the pieces together when we can. So, on to what it asks. The level curves for this surface are given by the equation. So we substitute z for k. So that's going to be k equals the square root of x squared plus y squared. So then, you know, to get rid of your square root, that becomes k squared equals x squared plus y squared, again, where k is any number. So in this case, the level of curves are going to be circles of radius k with the center at the origin. So we can graph these, and so for instance, we're going to be we need to ask ourselves, like, so when k equals 1, when k equals 2, different, you know, when k is different things, what will that look like? And from a 2-dimensional aspect, when k is 1, so let's say 1, 2, 3, 4, 1, 2, 3, 4. So when k is 1, from the 2-dimensional aspect, it would look like that. It would be a circle. I know. My drawing never looks like the best. Then this would be a circle when k is 2. Then when k is 3, we would have, a circle. Then when k is 4, well, that was a little bit better. And then so on. You get the idea. So now when we look at this 3-dimensional, and we look at this from our z, x, and y, so I'll label these. So we have k equals 1. Then you're going to have k equals 2. K equals 3. K equals 4 and 5. And we see this forms our cone. And again, I know, not the best drawing. So what you could put this in a calculator and look at the different pieces. You could pull it into looking at it. Let me see if I try to open the calculator. Let me make. Okay. Sometimes when I try to open up a different thing, it'll cut off the recording. So I'm hoping it doesn't. Okay. So again, so we had, let me show you. We had x squared plus a y squared equals, so we had equals 1. Okay. Now, well, I guess I'll shove 1. So then when we have 2, so this looks way better than my drawing, but so I'll show you. And so you see in the 2-dimensional what this looks like. Now it's not going if you extend it into 3D, it's from this aspect, it's not going to do what you want it to. It's going to give you these cylinders called but from looking at our 2-dimensional, it works. So now what happens when you put in with the z squared. So if we look at this three-dimensional, you see the cone, and so the original, so we had square root of x squared plus y squared. So you can see if you had typed it in the original way, it shows just the top of the hourglass, so the top of the cone, which is truly what we're looking at. We're not looking at the bottom part. So good. I'm glad that that worked. So you saw a better view of the two-dimensional. All right. So let's now, we can also think of contours in terms of intersections of the surface that's given by the z equals f of x, y, which is what we said, and that our plane is z equals k. So the contour will represent the intersection of the surface and the plane. So what we said is that you'll have your surface, and the contour will intersect the plane. So for functions of the form f of x, y, z, where we have f, x, y, and z, we'll occasionally look at a level surface. The equations of the level surface, again, are f of x, y, z equals k, where k is any number. So now we also, I'm going to start a new page, want to talk about traces. So traces were mentioned in the slideshow that I put up with the quadric surfaces, so I do encourage you to go back and look at that. So traces, in some ways these are similar to contours. We can think of contours as the intersection of the surface given by the z equals f of x, y. Traces of the surfaces are curves that represent the intersection. So traces of surfaces are curves that represent the intersection of the surface and the plane given by x equals a or y equals b. So let's take a look. Of course, you know, we want to look at an example. Okay, so let's see. I'm going to see if I can type this. It might look a little better. So sketch the traces of f of x, y equals 10 minus 4x squared. I think I'm going to have to write the squared. Minus y squared for the plane x equals 1 and y equals 2. Okay, so here's these directions. Let me go put my some squares in. All right, let me. Put in squared. Sorry, I should have just wrote it by hand. I thought this would make it look better. Okay, so sketch the traces of f of x, y. It should be equals Alright, this works. Okay. We'll start with x equals 1. We can get an equation for the trace by plugging x equals 1 into the equation. So we have z equals f of 1 comma y. So that would become 10 minus 4 times 1 squared minus y squared. So now that really is just z equals 10 minus 4, which is 6, minus y squared. And I'll graph this in a minute. This will be graphed in the plane by x equals 1. Okay. Let me sketch it and then we'll see if we can type it in so we can look at it good. So we have our let's get the picture going. There's no video. It's just sound. Y'all, my husband is crawling on the floor like I'm recording a video, and it's just sound. I'm not an artist, guys. This looks like a gumdrop, and it shouldn't. I might just have to draw it on the calculator. Anyway, so we have, I think I'm trying to make this too hard. Okay, anyway, let's shade this in green. This is the surface. So then, oh, no. So then this represents where we're going to have our parabola. Okay, so that looks, let's just show you. Hopefully it'll work in here. So say we have 10 minus 4x squared minus y squared. And so I will say when you type in stuff in Desmo, sometimes it'll look funny and you'll have to change your zoom until you get what you want it to look like. So this is what I'm looking at. And so this is kind of the view. And I was trying to draw this. And so now what we have is a trace that's going to form, it's going to like cut through. So that was, we had z equals 6 minus y squared. So you see kind of it cuts through. I had done mine kind of like as an entire sheet with the parabola within it, but this is probably a little bit better. So if we look at it this way, you see how this parabola, so what we just found was this parabola that's on this side, on the right. And so then when we substitute in, what was the other one? Y equals 2. When we substitute y equals 2, we're going to find a parabola on this side. So let's show what that work looks like. Because that's definitely, this is not it, a picture. Okay, so let's look when we're saying z equals f of x and y is 2. So that's 10 minus 4x squared minus 2 squared, which would give us z is equal to 10 minus 4, so 6 minus 4x squared. So let's just not look at my graph. Put in Desmos. So you type in the original and then your traces come from when x is 1 and this is when y is 2. Okay, so then we have z equals 6 minus 4x squared. And so, ooh, sorry. All right. And we have our a trace when y equals 2. Okay, so if we put them both together, you can see the difference. Okay, so I think I have a couple problems to attach, and then I do want to do a video on vector functions if I'm able. If not, at least get this, you know, if you've watched this video and practiced the practice problems, they're not to be turned in. You're not going to turn anything in until the next section, which will be vector functions.